Good morning, everybody. Welcome back to Math 105. Plan for today is we are going to begin our discussion of Standard 6 by talking about statements that are tautologies, statements that are contradictions, and individual statements that are contingencies, which is sort of going to give us a way to classify different types of mathematical statements based on how much of the time are they going to be true. And this is going to lead us into our discussion of kind of the classical rules, laws of logic, law of identity, law of excluded middle, law of contradiction, and will lead us nicely into our next standard, Standard 7, which will be all about logical syllogisms. Got my next office hours on Monday morning at 10 o'clock and from 2 to 3. As far as homework goes, the Standard 5 quiz was posted over the weekend and will be due Sunday, or was posted over the weekend, was posted yesterday and will be due Sunday night. So make sure you look at that quiz over the weekend. And as far as exam 1 goes, I thought a little bit more about it, and what I've decided to do is it is going to be take-home exam. And it's going to be just due to the nature of the beast. It's not going to be structured the same as the quizzes where you actually go and take it within Blackboard. The way I'm going to structure it is, as well as all the other exams, is it's going to be like a actual paper exam that you'll be asked to print out, write down your answers, and then you can scan, and then I'll ask you to scan in and then submit it through Blackboard. But you'll be submitting like a PDF document that contains all of your answers to each question. And because I am scanning things in, technical difficulties and all that, I won't limit it to strictly be a 1 hour exam. As far as once you open the file on Blackboard, you only have 1 hour to submit it or anything. I'll let you have up to a couple of days to decide when do you want to take the exam. But then I'll ask you to only work on it for an hour during that time, other than the process of printing it out and scanning it back in. I'll be sending out instructions with the exam that's very explicit about what are the expectations. But know that you will be asked to do the exam. I'll probably be sending it out something like Tuesday night and set a due date on it for Thursday night, is what I kind of expect. That's gone. Good math.
I have a medical exemption. Is that okay?
For today, yes. Let's talk after class. Let's see. Anybody have any questions or comments before we get started? Why are calendars always so nervous? Calendars are always nervous because they know their days are numbered. Okay, so the main subject I want to talk about today in Standard 6 is this idea of how you can classify a statement into one of 3 categories. So any statement P must be one of the following. The first kind of classification for a type of statement is if it's a tautology. Where a tautology is a statement that is true in every possible context. The second type is a contradiction. We've seen the word contradiction before, typically related to sets of statements back in Standard 1 that we said could not all be true at the same time. We could also have a single statement called the contradiction, where that contradiction is that statement must be false in every possible context. And finally, the third type, which is a contingency, where if every statement has to be one of these three things, tautologies are statements that are true all the time, contradictions are statements that are false all the time. What does that leave, do you think, for contingency?
They're true some of the time and false the rest.
Exactly. There's at least one context in which it's true. There's at least one context in which it's false. Let's write it this way. True in at least one context. Let's see. And false in at least one context. And so we've seen several examples of these throughout the semester. Statements that are sometimes true, but not always, depending on the state of the world, depending on the time of day in which you ask, depending on the person or type of object to which you're referring in a specific moment. Like if I were to say the statement, "This is red." Is that true or false? Well, depends on what this is. If it's if it's my shirt, then to which I'm referring, that would be a true statement. But if it's this piece of paper I'm referring to, it's a false statement. So, while we do have statements that can be always true and always false, there's also a lot of statements out there that we could make that really depend on the context in which you're making this statement. So let's look at a few examples. See if we can classify each one of these based on the category. What if I were to make the statement, "It is raining outside"? Which of these types of statements would that be? Is that an always true no matter when we say that? Is that always false no matter when we say that? Or would this be something that's true some of the time and false the rest of the time?
It's a contingency.
I would say so. This is going to be a contingency because it's sometimes true, sometimes false. Right now, it happens to be false in Hillsdale, Michigan at 8:08-ish a.m. But on other times and in other places, this could be a true statement. How about this one? It is raining outside, or it is not raining outside. It is raining outside, or it is not raining outside.
Tautology,
Why is that?
because either it is or isn't raining.
And so the or statement is going to have to be true either way?
Yeah.
I agree. Yeah. I would say this is a tautology because this or statement is always true. Regardless of the weather. Because as we've seen time and time again, for an or statement to be true, we just need at least one of the two pieces of it to be true. If it is raining, then the first piece is true. If it's not raining, then the second piece is true. Either way, our or statement is going to automatically be a true one. And then finally, it is raining outside, and it is not raining outside.
It's a contradiction because it's an and statement, but it's impossible for them both to be true.
Yeah. And just like in the previous statement, we said exactly one of these two things has to be true, which would make an or statement always true. But since it can't be raining and not raining at the same time, we are always going to have one of these pieces being false, and so the and statement is always false, making this a contradiction. Can't ever be true as an and statement, since exactly one piece will always be false. Yeah, these are kind of the three different ways in which we can evaluate a statement. Never true, meaning it's a contradiction. Always true, meaning it's a tautology. Contingency, or sometimes true, sometimes false, meaning it's a contingency. Any questions about kind of the meaning of any of these three? In that case, I'd like you to turn to the second page. I give you 5 more statements, and I would like you to see if you can classify each of these as being a tautology, a contradiction, or a contingency. Go ahead and take a couple minutes. If you feel comfortable doing so, you can talk to your neighbors. And we'll come back together here in a couple minutes and talk about these as a class. So what did you all think about this first one? John was awake from 4 to 5 a.m. and was not awake from 2 to 7 a.m.
Never be true.
Yeah, it can't possibly be true. If he's awake from 4 to 5 a.m., then there's at least 1 hour in here in which he can't possibly be not awake. So this is going to be a contradiction. It's never going to be true. If this is an or statement, this wouldn't be a contradiction, but as an and statement, it would have to be. If it is rainy and windy, then it is rainy.
It's a tautology,
Why is that?
because if it is raining and windy, so if P, then Q would be true. So it's saying if P, then Q.
I would say technically it's saying something like if P and Q, then P. Because if it's rainy and windy. But I would say either way, I agree. Yeah, this is going to be a tautology because in every circumstance under which this first piece is true, being rainy and windy, it also has to be true that the second one occurs. In every rainy and windy scenario, you're going to be in a rainy scenario. How about this one? Peanuts are healthy to eat.
I said this one was contingent because you have just like your sea salt peanuts that might be healthy, but you also have chocolate covered peanuts, which are not as healthy.
Okay, so there's different types of peanuts, some of which are not healthy. Yeah. You can also say it depends on the person that you're referring to. Maybe you have a peanut allergy, in which case all peanuts are not healthy to eat. And so there's kind of several different ways you can think about what's the context in looking at this statement. So I would say this one is going to be a contingency. I agree. Depends on the type of peanut, depends on the person or animal eating the peanuts, I would say. If my house is red or blue and isn't red, then it is blue.
I have it as in tautology because it's giving us a or statement, so it has to be either red or blue. And it's not red, so it has to be blue.
Yeah, I would agree. Our if statement's giving us two things. It's telling us our house is red or blue, meaning at least one of these has to be true. It has to be true that it's red, or it has to be true that it's blue, or potentially both. It isn't red, so we strike the red scenario. The only possibility left to us is going to be blue. I agree. And finally, our good old friend, this statement is false. I pulled this one on you back in standard one.
Contradiction,
Why is that?
because it literally can't exist within its own self. Like it contradicts itself. It can't be both true and false at the same time. Because if it's false, the statement is like
So you're saying that it's a contradiction, it always has to be false.
it's a paradox. So it's a contradiction.
Yeah, it's always false, which means it has to always be true.
I have it as a contingency because it can be true when context is false in another.
So it can be true, in which case it's false at the same time, and it can be false, so it can be true at the same time. This one's an oddball. A little bit hard to say.
I think there's no case which it can be either 100% true or 100% false. It's always like true and false, or false and true, right? So you can't say necessarily that's a contingency, because that means it's like 100% true at least once, or 100% false at least once. But like it's never that. It's always like true and false, or false and true. So it's just a paradox.
It's just a paradox, you can't even call it a contingency.
I don't think so.
It's not a mathematical statement.
It is not a mathematical statement. I'm going to agree. We can't classify this into one of these three categories because it is not even a statement to begin with. There is no circumstance under which it's true. There is no circumstance under which it's false either. Because if it's true, it has to be false, and that can't happen at the same time. If it's false, then it has to be true, which can't happen at the same time. It can't ever be true or false. And so this is me picking on you again. There is, unlike the rest of these, even with this one, a contradiction, you could just always say, oh yeah, this is false all the time. And okay, it's always false. That doesn't cause any concerns. It's just a false statement 100% of the time. Whereas this one, you can't even say it's false 100% of the time, I don't think, because that leads to a logical loophole where we're saying it's false 100% of the time and therefore it's true 100% of the time. Doesn't make sense to talk about. Yeah, nice job with these. Any questions or comments about classifying any of these statements? So let's see if we could do this symbolically, where we're given some symbolic statements and we're asked to determine whether it's a tautology, a contingency, or a contradiction. let's say we have some statement P, we don't know what it is, and I want to ask the question, is the statement P or not P a tautology, a contradiction, or a contingency?
A contingency,
Why is that?
because if P is true, then not P has to be false, and P is false, then not P has to be true.
I would agree, yeah. If P is true, not P has to be false. If P is false, not P has to be true. So in either case, what can we say about the or statement?
It's true.
I think the or statement will actually have to be true regardless, because whether or not P is false, true or false, one of these pieces is going to be true. I think this one is similar to the case of if statement P were to say, it is raining outside, then this would be saying it is raining outside or it is not raining, which we classified as tautology. But with these symbolic statements, I think it can be a lot harder to tell just from trying to look at them, piece together situations. So what is our nice handy dandy technique from Standard 5 that we have for kind of visualizing all the different circumstances under which a compound statement like this could be true or false? Yeah, we had truth tables. Truth tables are kind of our tool of picking apart a compound statement and being able to look at the circumstances under which it's true or which it's false. So let's see if we can make a truth table for this statement. So I'm going to draw a truth table. I'll make a column for P. I'll make a column for P or not P. What might be a useful stepping stone column in the middle that'll help us get from P to P or not P?
Not P.
Yeah, just a not P. If we have a P's and our not P's, then we can use that to get P or not P pretty quickly. So P has only two possibilities. We only have one pre-filled column here. So it's going to be, is P true or false? We don't have to make a column for Q here because our compound statement is only referring to a single P. If P is true, not P is going to be false. If P is false, not P is going to be true. And if P is true and not P is false, is P or not P going to evaluate to true or false in this scenario?
It's going to be true because for an or statement, only one piece it has to be true or to be true.
Yeah, we have an or statement where at least one of the two pieces is true. Therefore, our or statement is going to evaluate to true. How about if P is false and not P is true? Is P or not P going to be true or false in that circumstance? What's that? Someone said something.
True.
Why is that?
Because it's an or statement, so if your second is true, then the entire statement will be true.
Yeah, same as the first line. We have an or statement where one of the two pieces is true. That's enough to make our or statement true. And so, if we look at all the different circumstances for P or not P, in every scenario, P or not P is going to evaluate to true. Whether P itself is true or false, P or not P will always evaluate to true. And so that's how we know we have a tautology, is because in every possible context, whether or not P, the original statement was true or false, in every possible context, P or not P evaluates to true. That's going to be what tells us we have a tautology. So it's going to be a tautology. Tautology, a little bit of a hard word to spell. Since the column in the truth table is always true. So the fact that this column has no falses in it at all means there's no scenarios where the statement could be false. It's 100% of the time going to be true. Therefore, it will be a tautology. And in general, you can always do this with the statement. You could say, if you were to draw the column in the truth table for that statement and you get all truths, that's enough to tell you you have a tautology on your hands. True in every circumstance. Any questions about that? Let's take another look at one as a class, and I'll let you do a couple of these on your own. I want to look at the statement P and Q implies not P. This one's a bit harder to me because we have sort of a compound. I see two ands, one negation, one implication that's kind of being built in part of this sentence. This would be like trying to classify the statement, this apple is red and this apple is juicy, and if the apple is juicy, then it's not red. I'll have to try, for me at least, to wrap my mind around all at once.
I looked at it and said it's a contradiction.
Well, good for you. You think this is a contradiction?
I do.
Okay, explain yourself.
Because we start with P and Q, and then we say Q implies not P, which means if we have Q, for this to be true, we'd have to have P and not P, which is impossible.
In order for this to, and this part requires that both P and Q are true, but this part is saying since Q is true, not P also has to be true in order for the and statement to be true. And so you'd end up in a situation where both P and not P are both going to end up having to be true.
Right.
It's a lot to think about. I think I agree with your logic. But let's see if we could prove this using a truth table. So if we have a statement that has all truths, we said that comes out to a tautology from the truth table. What do you think should be true about the truth table for this statement if it were to be a contradiction? What do you think that column in the truth table would look like?
The two sides can never share a truth in the same instance.
Yeah, so that particular column would always be
False.
like we're going to get a column. We should get a column full of falses. So let's see if we can show this. So we'll have a P and Q will be our kind of pre-filled columns. True, true, false, false, true, false, true, false. So here we've accounted for all our possibilities with P and Q. I think we can go ahead and make a column for P and Q. What would the P and Q column look like here?
True, false, false, false.
True, false, false, false. Only true in the scenario where both P and Q are true. So that's one of our two pieces. The other piece is going to be Q implies not P. So what would be a useful stepping stone column to include in the middle there?
Not P.
Yeah, just a not P. Because then we'll have a Q column, a not P column. We can use that to help us find a if Q then not P column. So our P column is true, true, false, false. So our not P column is going to be false, false, true, true. And so now we can use that to find a column for Q implies not P. If Q is true and not P is false, what is if Q then not P going to evaluate to? If we're saying first thing is true, second thing is false, is the implication going to be true or false?
False.
It's going to be false. That was our scenario number 2, the one time an implication can be false. On the other hand, if Q is false and not P is also false, what can we say about Q and not P? Then it's going to get our seal of approval, because if false thing then false thing is always a true implication, as we've seen. If Q and P, not P are both true, I'll answer that one. This one's true. And finally, if Q is false and not P is true, what does that tell us about Q implies not P? If false thing, then true thing. I think it's going to be true. This was our scenario number 3 where you didn't win the tennis match, but you still got ice cream because I took pity on you. I didn't break my promise by saying if you win, then you get ice cream, just by giving you ice cream even though you didn't win. The only way to break that promise is you win, but you don't get ice cream. If the first thing is true, but the second thing is false, it's the only way to break the implication. So now we have columns for P and Q. We also have a column for Q implies not P. And so if first thing is true, so now we're comparing these two columns. If first statement is true and second statement is false, what's our compound and statement going to evaluate to? If P and Q evaluates to true and Q implies not P evaluates to false.
No, it's going to be false.
I think so. I think this one's going to be false. Because it's an and statement. True thing and false thing will always evaluate to false. How about false thing and true thing?
It's gonna be false.
It's going to be false for the same reason. False, true, going to give us false. False, true, going to give us false. And so I think I agree. This original statement is always going to be false in all possible circumstances, regardless of the P and the Q. So the fact that we get a column full of falses tells us that our statement is a contradiction. Since in all contexts, this statement is false. Neato burrito. Any questions about either of these examples? So if you're looking at a truth table and the column for your statement is always true, we said it's a tautology. If it's always false, we said it's a contradiction. What do you think the column would look like for a contingency statement? What would a column for a contingency statement look like?
A mix of true and false.
A mix of true and false. I would agree. There's at least one true in there, and there's at least one false in there. All right, go ahead and take a couple minutes, and I'm going to see, I'd like for you all to try and work through the next couple on your own. See if you can determine if P implies Q and Q implies P, as well as P and Q or not Q, whether those statements are tautologies, contradictions, or contingencies. We'll come back together in a few minutes here, once you've had a chance to look at the truth tables. one hint I might give you is, for the first one, there is a shortcut method. If you've finished drawing the truth tables and come up with an answer for these two statements, see if you can think for a minute about what the shortcut method might be for the first one. Because I think P implies Q and Q implies P is a statement we've seen before in a different way. Okay, so let's come back in and see if we can come to an agreement on either of these. So our first statement says P implies Q and Q implies P. So I went ahead and started the truth table. I filled in columns for P and Q in both contexts. For our first truth table, P implies Q and Q implies P. What were your all's strategies?
Well, you saw it the long way.
Okay, what's the long? How did you start the long way?
You saw P implies Q and Q implies P, and then you use that to solve the whole statement.
Okay, so you made a column for each individual implication, and then another one for the and statement. Cool. Let's see what happens. So if we look at P implies Q, seen this one before. That one's going to be true, false, true, true. If we look at Q implies P, what did that column end up looking like?
True, false, true.
True, true, false, true. And so finally, if we did the and statement, P implies Q and Q implies P. Somebody else, what would the column for that look like? If we have a true, false, true, true column, and a true, true, false, true column, what would the column look like if we tried to combine those with an and statement?
True, false, false, true.
True, false, false, true. I agree. And so if the column we get for P implies Q and Q implies P comes out to true, false, false, true, what can we say about our and double implication statement?
It's a contingency.
It's going to be a contingency. going to be a contingency. Because it is sometimes true, sometimes false. Was anybody able to find a shortcut method for this? Kind of hinted at it, that there might be a quicker way to do that using something we've already seen before. But what might be a shortcut that we could use here?
You can cut out the three right columns and replace it and prove logical equivalency between P and Q. So P and Q, whenever they're logically equivalent, they're true, they have the same truth value at the same time, and it comes out to the same truth pattern as proving the and statement.
Yeah. We've seen this P implies Q and Q implies P before. That was something from the last packet that we showed is logically equivalent to saying P and Q are logically equivalent. In fact, we've already seen this whole statement means the same thing mathematically as saying P and Q are logically equivalent. And so, and here's the cool part, once we've shown a result in here, once we've proven a result, we're allowed to just straight up use it. We don't have to go through this argument again. Once we've shown if P then Q and if Q then P is logically equivalent to P is logically equivalent to Q. Once we've shown that once, we never have to prove it again, unless I ask you to on an exam or quiz or something. We could just straight up use that result. And so, in order to do that, we could just say, oh, we could just make a truth table. We'll still have our same P and Q columns. And now, just use the P being logically equivalent to Q, which is true if P and Q are both true or both false, and false otherwise. We get the same column in the end, which still tells us we have a contingency. But doing it in this way, using the thing that we've already shown is logically equivalent to P implies Q and Q implies P, made it a little bit faster for us. Now we only needed a truth table with 3 columns as opposed to one with 5 columns. Yeah, nice observation. And so, if you ever recognize me giving you a statement that's logically equivalent to something we've already looked at, you can certainly just use the thing we've already looked at instead, and maybe save yourself a couple steps that way. That's totally legit. Okay, how about this last one? I think this last one might be a little bit different. P and Q or not P or not Q. Holy Toledo.
I have it as a tautology.
You had it out as a tautology? Awesome. I did too. What was your first column after the P and Q columns?
I did the P and Q.
Okay, just went right to the first piece of the OR. Makes sense to me. So if we do a P and Q, we're going to get a true, false, false, false. Might be helpful to have a couple other columns before making one for not P or not Q. So what could we have as columns first before getting to a column for not P or not Q?
I'm going to call for not P and
Yeah, just the individual negations. False, false, true, true. False, true, false, true. And so then we can combine those with an or statement. If they're both false, the or statement's false, but in every other context, at least one of them is true. And now we can make a column for the whole thing, P and Q or not P or not Q. So let's see, we're using these 2 columns. If the first piece is true and the second piece is false, our or statement is going to be true. If our first column's false and our second column's true, the or statement will be. If the first column's false and the second column's true, well, other than the exact same 2 scenarios, false, true. we end up with a column that is indeed full of truths. And so it will give us a tautology.
Since we know that there's a negation, they're always going to be, it's basically the same P or not P. And we've already proved what we can consider the negation. We need to do all that work, so I'm asking.
Oh, you had another shortcut method.
Well, we know that the second one is the negation of the first one. If we just prove that there's a negation, we have to write out all of them stuff.
So when you say the second one's the negation of the first one, to be clear, you're saying this piece is the negation of this piece, right? Yeah, I would totally agree. We could find a shortcut method for this one as well by saying P or Q, no, P and Q, or not P or not Q. So it sounds like your claim is that this is logically equivalent to saying P and Q or negation of P or Q. And that's a tautology because you're just saying thing or negation of same thing. This is just like the P or not P example. Let's call it R. We could say if R is equal to the statement P and Q. Oh, yes, you're right. Sorry. Too many ors and ands and negations for me to try and juggle in this one. But you're right. So this is saying P and Q or negation of the same thing, P and Q. So if we let R be equal to P and Q, this is going to be the same thing as saying R or not R, which we've already seen is a tautology.
So if we just write out the negative into a single variable and prove that that's how it is, as a single variable, we don't have to do all that.
Absolutely. Nice thinking there. Yeah, it's because we're using something we're using a couple things here that we've already proven, namely that the negation of P and Q is not P or not Q. We're using that, which we proved. We talked about in Standard 3 and proved in Standard 5. That's one of De Morgan's laws. We're also using the fact that we've already proven statement or not, same statement, is a tautology. Combining those facts will help us get to see this has to be a tautology. That's a very nice observation, though. I'm glad you noticed that. So you can always brute force it with all of these just by drawing a truth table from scratch. But if you notice that you have shortcut methods available to you by, say, rewriting the original statement as something you already know to be logically equivalent, then oftentimes you can make your work a lot easier. So that maybe you can just use a simpler truth table, or maybe you don't even have to draw a truth table at all. Any questions or comments about any of that? I'll let you go a minute early. So on Monday, we are going to start by looking at the 3 classical laws of logic, and we will be talking about what Plato and Aristotle have to say about all of this. Hope you all have a good weekend. Don't forget to do Standard 5 quiz, and I will talk to you on Monday.
Thank you.
Thank you.
One super quick question, and it'll solve